Give a name here, blurring edge and sharpening. So let's do that. And then let's import certain packages that are required. For example, let's go for NumPy, import NumPy as np import matplotlib.pyplot as plt, import cv2 if we really need certain functions from OpenCV. And for convolution right now, let's import a package from SciPy signal. From SciPy, import signal. So let's see if all imports work. Yeah, they work. Let's copy the path of the image that we were working with before. So let's do that. So that's our image. And remember, this particular image has 4 channels. So let's pick the first 3 channels, the RGB channels, and copy that into our image. So that's our image. Let's apply these operations, image blurring and sharpening and all that stuff on grayscale image. So let's convert that image to grayscale. mgray is cv2 dot cvt color, cvt color, and in there I passed m, and then I have cv2 dot color underscore RGB to gray, and hopefully this should give us the grayscale image. Now I design a mask or a filter that basically I will apply that filter onto this image, and it will basically blurs the image. So let me design a blurring filter or smoothing mask. So smoothing mask is, let's say, np.once. Let me generate a mask, and let me generate a larger mask. If the mask is bigger and bigger in size, then you'll be having, for example, more and more blurring. One way to achieve more and more blurring is to increase the size of the mask. The other way is to apply the mask repeatedly on blurred images, and you get more blurring. Further, we need this mask to have a sum of 1, so we divide the mask by its sum. So that's our smoothing mask. Next, we convolve this mask, convolve our image with this mask. So mblurred, let's say mblurred is signal dot. So yeah, let's have a copy of our so mblurred is equal to signal dot convolve 2D. Yeah, that's a function there in signal. mgray, and then we have this mask, which is smoothing mask or smoothing filter. Then we have to give a couple of other arguments. For example, what do you want to do on boundary? What happens, there are several ways to do stuff on boundary. For example, on boundary we can zero pad, and one way to deal with the boundary pixels is to just symmetrically copying the intensities rather than zeros, and that is also called symmetric reflectance. Then the mode, whether you want the resultant size to be the same or different, because the convolution in its definition mathematically, it can give different sized image. So that's our blurred image for now. So that's our blurred image. It will take some time because this convolution operation is a little expensive in time. So now let's have figure our AX1, which is our original image, AX2, that is our blurred image, is equal to plt dot subplots. And here we have, let's say, the subplot of size 2, fig size equals to, let's say, 10 and 15. Let's say these are the sizes, and then we have ax1.imshow, and let's say that is our actual image, which is in gray, and cmap is gray. Then we can have ax2.imshow, that is our blurred image. So that's a im blurred, and cmap again is gray. So let's see if the image indeed becomes blurred or not. So you might be seeing this image is much more sharper than this particular image, and the values, for example, if you see on this area and this area, they are smoothed out. So image blurring actually happens. If you, for example, want to blur the image more, one way is to increase the size of the filter. The other way is to blur the blurred image again and again with the same filter, and you will get more and more blurring. This does not only apply to the whole image. You can have a patch of the image, for example, a face of a person. If you want to blur that, you may have a face detector in the image, and you detect the bounding box of the face, and just for that area, you can blur that area. And that is what we call as face blurring, or a particular region blurring in the image. So, but the crux of all that, or the basic building block of all that, is convolution. We design a mask, and then we convolve and do some additional processing, and we get the blurred image. In the next piece of code, we are actually going to work on basically edge detection. So let's make certain masks. Let's say X mask. Let me make the X mask np.array, and that is a mask of, for example, -1, 0, 1, and then we have another -1, 0, and 1, and then we have another, for example, -1, 0, and 1. That's a mask. It should be a 2D mask, so let me make it a 2D mask. So that's our mask, X mask, and Y mask can just be the transpose of X mask. So it is X mask dot transpose dot copy, just to make sure that both do not change if there is ever an operation that changes the mask values. So these are our masks. Now we convolve the basically our original grayscale image with these masks, and let's see how can we detect different kind of edges. So let's say fx is signal dot convolve 2D convolution imgray with x mask. Boundary is the same, symmetric, and the mode is same. So the same size of output. And let's copy that for y as well, because the same operation will go for y. And here we go for y. We have this y, the same image convolved with y mask, and rest of the story is same. So that's our fx and fy. If you see the shape of fx, that is exactly the same as the shape of imgray. And the same is true for fy as well. So now we define our gradient magnitude. So the gradient magnitude basically is equal to fx squared plus fy squared pixel wise, and then a square root that actually defines the gradient magnitude. So 0.5, which is for square root. So that's our gradient magnitude. If you just see, if you just visualize this matrix, that is not an image, that's a matrix. But you can visualize that as well by show in gradient magnitude cmap as equal to gray. You'll be seeing a more highlightings at the pixels where the intensity change is higher. We can threshold this value. For example, let's compute the threshold. For example, threshold might be gm dot max um, um, and minus 2 times, for example, gm dot std, for example. So that might be a threshold. Let's see what the threshold value is. In this particular case, the threshold value is 1.18. Maybe we can change the threshold. Maybe, for example, we can reduce the threshold by, let's say, 3 or 4, maybe, 4 standard deviation, and we may get this one. So let's see what is the edge image. So edge image might be gradient magnitude greater than our threshold. And we can then plot our edge image. plt.mshow edge, and the color map is gray. So now you might be seeing, oh, the threshold is really hard. We need to set the threshold a bit low. Only a few edges, very strong edges, are being shown. So let's for example here, let's set the threshold as is greater than, let's say, 1, and see what do we get. We get some edges here. Yeah, let's reduce the threshold further, for example 0.5, and see if we can have more edges. Selecting this threshold is really a difficult task, and there is no automatic way to set the thresholds. For example, we can have a threshold, more loose threshold, and we can have this particular image, that is the edge image. There are more sophisticated ways for selecting these thresholds. Applying the thresholds, multi-level thresholds called hysteresis thresholding, and to get more thin edges by applying non-maximus pressure and stuff. But that's what the basic flow of edge detection is. And if you see, the backbone of this procedure is again convolution. Next, we move to image sharpening. What we will do is we will pick the blurred image, and we will add a portion of gradient magnitude to the blurred image, and we will get a more sharper image as we expected. So sharper, sharped, might be equal to the blurred image, blurred, plus some factor, let's say 5 times the gradient magnitude. And that should give us the sharp image. That's one way of producing a sharp image, although there are several others. So let's see, let's plot the sharp image and the blurred image side by side and see whether it gets sharped or not. So fig ax1, ax2 equal to plt.subplots 1 by 2, and fig size equal, let's say, 10 to 15, and ax1.mshow, let's say, first we display a blurred image on the left, cmap equals gray, and then we display our sharped image that we think is sharped, cmap equals gray, and see if that works. Oh, why is that? What has happened? Gradient magnitude and that, it just blows away everything. That's a blur image. That should be a sharped image. What has happened? Maybe this gradient magnitude has just changed its value. Maybe that's the so let me compute the gradient magnitude again, and just to think, let me just go back and apply these things and get this again and compute the gradient magnitude again, just to be sure that this has not changed. So if I now apply gradient magnitude here, let's say 5 times, or maybe just 1 times gradient magnitude, then what will happen? Let's see. Yeah. So you can now see a more sharper effect here. Yeah. So that's the sharp version of this one. Maybe we should reduce the quantity of sharpness by multiplying this with a portion rather than as a whole. So this parameter must be defined as well. So now you can see a more sharper variant, less sharper than earlier variant, but a sharper variant than this blurred image. For example, if you focus on this area, it has more detail rather than this one. And again, in this image sharpening operation, as well as you have seen in this video, we took the advantage of computing gradient magnitude, which actually is a result of convolution. So the purpose of showing you these operations, image blurring, image sharpening, and edge detection, all these, is basically to highlight the importance of convolution, that this convolution operation can actually be used for detecting several different kind of structures in different kind of images. And that indeed becomes the basic building block in convolutional neural networks as well. So in the next video, I will show you that these edge detections and low-level features, they actually can be combined to give more basically more robust kind of high-level shapes or higher-level objects. And we will see that in classical computer vision techniques, how these edge detection, how the result of these edge detections, or low-level features, they actually give rise to high-level object detection. So hope to see you in the next video.